Okay, so here's why this lecture is exciting to you guys, because you're what, 8 weeks into your first linear algebra course, and I will tell you about something that's actually a recent discovery. It was discovered by Strang just a few years ago, and it's a remarkable identity for its simplicity. So I'll get to that. It is a matrix decomposition, and let me just remind you why we're excited about matrix decompositions. And we're excited about matrix decompositions for 3 reasons. Number one, they follow the spirit of mathematics of representing complicated things as combinations of simple things. We've already seen this idea when it comes to decomposition with respect to a basis, but all matrix decompositions follow the same pattern. Now I'll say a few more words about each one of these, but in all cases you have a complicated arbitrary matrix on the left, and it has no structure, we don't quite understand what it's doing, and so on. And it is represented as a product, so matrix identities, decompositions are all about products. And it's represented as products of either simple matrices or highly structured matrices. So they're all about insight. So representing complicated things by combinations of simple things is always a positive thing to do in all walks of life, but especially mathematics. So that's number one reason why we like matrix decomposition. Number two, we really like algebra. It's great to use words, it's great to use logic. It's great to talk about algorithms. All of these things are great. But it's a totally different level, I think, when an algorithm or an idea or a recipe or a theorem is captured by an algebraic identity, because it awakens in us all sorts of ideas that are just followed by analogy with the rules of algebra that we learned from 4th grade on. And we've already experienced this with the eigenvalue decomposition. So we derive this, and then we realize that when a matrix is represented in this form, it's just a joy to multiply A by itself and raise A to any power, because that makes X and X inverse come together and multiply to produce the identity and therefore disappear. So it's a very it's a very satisfying process to use the eigenvalue decomposition. So that was just one example. But the advantages of expressing ideas in the algebraic language is very powerful and leads to a lot of great things where you can just turn on an entirely new part of your brain, or sometimes maybe not have to turn it on, because when algebra is involved, sometimes it feels like the rules of algebra take the process over, and it just feels like you're watching a movie where the action is happening for you and you don't have to actively think. Sometimes doing algebra feels that way, and I like that about algebra also. Okay, that's the reason number 2 why we like matrix decompositions. And reason number 3 is that we really like formulas. And there is something that's very self-contained and beautiful about formulas. They're sort of like, I don't know, Egyptian pyramids that are just exist, and sometimes it's not clear where they came from, how they were constructed, but we just admire them for their beauty and their mystery, because there's some feeling of immortality associated with formulas. I'll give you just a couple examples. If you think of Isaac Newton, you immediately think of F equals ma. When you think of Einstein, you immediately think of how about Euler? Euler is known for a lot of things and lots of formulas, but there is one formula, actually there are many formulas that are called the Euler formula, but there's one in particular. I will actually write it down because I think there are some parallels. This belongs on the board in this lecture because you'll see some similarities between this formula, actually I'll mention what those similarities are almost right away, and this decomposition. So Strang has a lot of very important accomplishments that are associated with his name already. There's the finite element method, a numerical method for solving partial differential equations. FEM theory is associated with his name. Wavelet theory, a number of other things. So now there's a formula, and I think that this one will be more instantly recognizable and more quick to associate with his name than some of his other accomplishments. One other thing that I'll say about this decomposition. Of all the decompositions that you have on the board, this one is the simplest. And that's also remarkable because we live in a world where things are becoming more and more complicated. And I think, for the most part, it's out of necessity. I think our cars are becoming more sophisticated, our computers, our phones, our rockets, our weapons, our communications, everything's becoming more complicated out of necessity. But in science, unfortunately, there's also a tendency to make things more complicated. And that's usually explained by a lack of talent. If you need to produce something and you're not very talented, you're just going to take something that already exists and make it more complicated. Add one more term, add a little bit of this, sprinkle a little bit of that, and make it your own that way. So there's this artificial tendency towards greater complexity. So when something comes along which is actually simpler, that's anything that came before it, that's like a breath of fresh air. And that's where the similarity between this and this formula, Euler's celebrated formula, exists. Because what they have in common is their simplicity and how they summarize the information that was already available beforehand. Everything that these formulas summarized was in plain sight in front of everybody. And in retrospect, these formulas seem inevitable, but it took Euler to come up with this formula, and it took Strang and his talent to come up with this formula. And I still remember sitting in his office talking about how my linear algebra course at Drexel is going and sharing some of the problems that I had on midterms. And he just mentioned this, and he said, "Did you notice that?" And he mentioned this fact, which this lecture is about, and you'll find out. And actually you already know about it, and you'll realize it as soon as I say it. And I immediately saw that it's true because it's so simple, and I couldn't believe that I never thought of it before, but I never have. Okay, so that's what's so remarkable about this decomposition, is that it's the simplest of them all, and maybe the most central and pivotal of them all. So, let me just say a few words about each one of these decompositions, just so that you see where that one fits. So the LU decomposition.
It's tomorrow.
Well, you'll be really prepared.
Yeah.
So the LU decomposition, we barely talked about it. I think I will assign studying it over the Thanksgiving break. But it is essentially a matrix reflection of the Gaussian elimination process. When you start out with a matrix, and by the time you identify all the pivots and eliminate everything below them, you end up with essentially an upper triangular matrix. And so that's called the matrix U. So that's what's left after you're done with Gaussian elimination, but not back substitution. And L is the summary of all the steps that it takes to do Gaussian elimination. And it's the inverse of all the steps. So when you put them together, what's left of the matrix after Gaussian elimination and the reconstruction of all the steps, you get back to A. The eigenvalue decomposition, also known as the spectral decomposition, that's the decomposition we're working on right now. We already said a few words even in this lecture today about it, but yeah. The next comes, they're actually all related, these three, but the singular value decomposition, the SVD, instead of the eigenvalue decomposition, it's the singular value decomposition. It's actually probably the most important formula right now. The Google algorithm is based on this decomposition, and a lot of the big data and machine learning is based on this formula, in this decomposition. The singular value decomposition certainly occupies an important role in linear algebra 2. And then a decomposition related, or maybe the one that precedes the singular value decomposition, is known as QR decomposition. These two are extremely geometric. I would think of the spectral or eigenvalue decomposition as very algebraic, even though it does have a geometric interpretation, and we already talked about it today. But it's essentially an algebraic idea. Eigenvalues are an algebraic idea, and this is an algebraic decomposition. And these two are very much geometric decomposition. This decomposition has to do with taking an arbitrary set of linearly independent vectors and then modifying them to make them orthogonal. So it has to do with taking an arbitrary set of 3 vectors, linearly independent vectors, not 3, but however many linearly independent vectors you want, and then just making these sorts of adjustments to make it not just orthogonal, but orthonormal. All orthogonal and unit length. Okay, so now, of all the central and most basic decompositions in linear algebra that you have here, this one is the most elementary and the simplest, and maybe the most important. So, let me just dive right into it. And what we're going to do right now is I'll write down a matrix, and we'll figure out its row-reduced echelon form. So the matrix itself will be A. The row-reduced echelon form that results from the matrix A will be the matrix R. And you'll guess what the matrix C is and why it's called C. So it's not perfect because I've got to sneak in another matrix in here, but I think I have just enough space.
Can we do it the fast way?
Yeah, of course, we
Alright,
have to
1,
do
0, 0,
1, 0, 0,
3, 0, 0,
3, 0, 0.
0, 1, 0.
Yes. Sorry, I'm
You
sorry I
doubted
doubted you. I'm
Alright.
sorry.
10, 1, 0. 0, 0.
What is?
Yes, we are.
0, 0, 0. And?
0, 0, 1.
0, 0, 1. Okay. Just a quick reminder for why this works. It's because whatever relationships among the columns are present in the original matrix are also present in the eventual matrix. So if this column was 3 times the first column in the original matrix, it's going to be 3 times the first column in the eventual matrix. And because the first column is not the 0 column, so in other words, it's linearly independent when you consider it by itself, this is the first pivot column, so it's 1, 0, 0. This is the next pivot column, so it has to be 0, 1, 0. This has the same relationship to the columns, whatever relationship this column has to the columns in this matrix, that's what this column has, that's this, I lost track of my English sentence, but this column will have the same relationship to these 2 columns in the eventual matrix. Same thing for the 0 column. And finally, because of its quirkiness, we can tell that it's linearly independent from the columns that came before it. So it's going to be the 3rd pivot column, which is 0, 0, 1. All right. So this is the matrix A, and this is the matrix R. So you can almost think of it as this matrix exposes the relationships among the columns, or documents the relationships among the columns. So another way to do it is to actually, and that is to record the relationship among the columns, is to write out the null space. For this matrix or this matrix, it's the same null space. So we could do it this way, but we don't have to take that final step, because we know that the null space is very easy to determine from the row-reduced echelon form. That's actually the whole point of the row-reduced echelon form, to expose, and we will say record, the relationships among the columns. So when it comes to my IKEA furniture analogy, when you have to reconstruct the matrix from its, let's say, column space and null space, this will be the one application of the decomposition that I'll show you. This is the instructions. This tells you how to put things back together. But where are the pieces? So here is the key observation. So we're taking the pivot columns of the original matrix. These are the columns that span the column space. I mean, there are other combinations of columns that span the column space, but these are the earliest ones, the leftmost ones that we can use to span the column space, and we organize them into this matrix. Now let's just take a moment to see why that works. If we'll look at this product, you will see that this is like automated IKEA instructions that put the pieces that came in the box in just the right combinations and in the right place in the matrix. Let's look at this column by column. When we multiply this matrix by the first column, well, the first column is 1, 0, 0. What does it say? It says, take the first column from this matrix and put it in the first column of the answer. And there it is, this column is restored. Now, what does the second column tell us to do? It tells us to do the same thing, just 3 times as much, and make it the second column. So in other words, it'll make the second column 3 times the first column, and boom, the second column is restored. And what does the third column here tell us? I'm going to go through all of it. It says pick out the second column. This column is a column picker. Pick out the second column and put it in the third position. And so we extract the second column from here. That's what that column does, and puts it in the third position. And now this column is restored. Now what does this column tell us to put in the fourth position? It's the fourth column. It tells us to take 10 of the first column plus 1 of the second, making it 15, 24, 41. Well, here it is. It just does precisely what needs to be done to reconstitute the matrix A. What does the 0 column tell us to do? It tells us to ignore everything and to just put the 0 column in the 5th position. And what does the final column tell us to do? It tells us to, well, this is also a column picker. It says pick out the third column from this matrix and put it in the 6th position. So it picks out this column from here and puts it right here. So do you see how it's almost like making orange juice? This is the reduction of orange juice. The orange juice powder, does it get reduced to powder or pulp? And then you add water in just the right proportion, except with much greater sophistication. And voila, you have your orange juice back. So this is almost like the complete reduction of the matrix. Instead of using the entire column, all of the columns, we just pick out the columns responsible for spanning the column space. And then we combine it with a matrix that tells us exactly how to organize them so that not only is the column space represented correctly, but also the relationships among the columns. So this, of course, is the matrix A. This is the matrix C. And this is the matrix R. And there is your A equals CR. Would you agree that this is probably simpler than you would expect any new research or any new discovery to be?
Mm-hmm. How useful is it though?
How useful is it though? It is very useful. So I'll give you one example of its usefulness. And that will also be in the context of the sorts of problems that I've been giving you. But its usefulness goes beyond this. And Gil has recorded a few videos where he talks about this. So
Gil?
Gil Strang.
Oh. Wait, that's his first name?
Yeah, Gil.
Okay, that makes sense.
Gilbert. Actually, that's his middle name.
Oh.
That's the name he goes by. So he has recorded a few videos on this. So I'll let him speak for his decomposition. He can do it much better than me. But let me remind you, here's an application for this course. I've been giving you these problems where I specify the column space, which I have been calling R, but now I have to call it C. Right? You understand why it's C. C for columns, and R for row-reduced echelon form. So I've been calling column space R. I can no longer do that in this lecture, so I will say, I would provide you with the column space of the matrix, and I would provide you with the null space of the matrix, and I would ask you to reconstruct the matrix. And the way you guys did it was very nice and algorithmic. You used insight and logic, and you just built the columns one by one, and you reinterpreted the null space as instructions for exactly how to organize the columns and how to relate them properly, and you all did great on the midterm. So that's certainly one way to do it. But now you can actually do it algebraically without using insight. You know, it's kind of interesting that I am celebrating lack of creativity, right? When there is a tool that allows us to be less creative and less insightful and less talented to perform a certain task, you know, like the table saw or the router or the computer and so on. That's a celebration of the tool, you know, and that's the way of progress. Okay, so now I think we can try and perform this task and not only produce one matrix that does it, but produce all possible matrices that have this column space and this null space. Now, I still can't do it cleanly, but I think there'll be a way to do it cleanly from this. So how would I approach this? Well, I'm just going to tell you schematically how I'm going to do this. Now, whatever the columns I have, oh yeah, there's one other thing I have to tell you about this decomposition, which I will. But here's an application. Whatever columns I have, I'll just combine into this matrix C. Okay? And whatever the null space I'm presented with, now you've been working on this exercise and you've been doing it algorithmically and maybe intuitively, but I would translate this into row-reduced echelon form. That's what a row-reduced echelon form is, right? And then all I'll do is multiply these two matrices together, and voila. I have a matrix that has a prescribed column space and prescribed null space. Okay, that's one way. That's one thing you can do. Now suppose you wanted to produce all possible matrices that have this column space and this null space. This is where it becomes a little bit less clean, but if you think about it, I can stick in here any invertible, well, just using the dimensions we're using now, 3 by 3 matrix. If I put in here, in the middle here, any invertible 3 by 3 matrix, what it's going to do is create 3 linearly independent linear combinations of these 3 columns, and will therefore preserve the column space of this matrix. I was thinking about that also, so you'll just say this matrix is 1, 1, 1, right? This is a lower triangular matrix, right? With non-zero numbers on the diagonal, and this can be anything you want. So this can be anything you want, this can be anything you want. Actually, I would put ones into this matrix, and this can be anything you want as long as they're non-zero numbers. So that's not bad.
Would that be the
LU decomposition. Anyway, this is a little fuzzy, but it's accurate to say that any invertible 3 by 3 matrix, it just doesn't reduce the problem to its degrees of freedom. Okay, let me tell you one other thing about this, this decomposition. What would happen, we could even come back to this matrix, if the last column, can I bring it back? I'm actually going to bring it back. And actually, I'll make this last column linearly dependent of the ones that came before it. Zero, zero, and finally 1. Did I miss something? 1, 2, 3,
No, it's
4,
1,
5,
0, 10. Wait, no, you're right.
Yeah. 0. Okay.
You just wrote them cramped.
Sorry?
You just wrote them a little squished.
Yeah, it's a little squished, but there it is. Let's unsquish them. 1, 0, 10. And then there's an entire row of all zeros, right? And then here, we only have space for 2 columns because there are only 2 linearly independent columns. 1, 2, 4, 5, 4, 1, right? And so I guess that would be it for the matrix C, right? And the big problem with this is that I now have an incompatible product. This is 3 by 2, but this is not 2 by something. It's not 2 by 6. It's 3 by 6.
Can't you just put in any number?
Well, here we go. So what do? We can do 3 things here. 3 things that we can do. So first of all, let me just highlight that this is incompatible. It's 3 by 2 by 3 by 6. So 2 and 3 are incompatible dimensions. So I'm already getting ideas for what you can do. Perhaps the cleanest thing to do is to actually eliminate the 3rd row here. How about that? That's one thing you can certainly do. That is not a row that gives us any information. So we can just eliminate it. And then we're good. It's compatible and actually produces this matrix. Do you guys agree? That's kind of clean. Less data, same result. That's one idea. What's another idea? I actually don't know which one Gil prefers, so it would be interesting to watch his videos again and see which one he prefers. So that's one idea. What's another idea? Another possible solution is to put zeros here, since it doesn't matter. Now it's compatible.
Zeros or any number you want.
So we have idea 1. Now this was idea 2A, and then Chris's is idea 2B, which is put anything we want. Right? I'll give you a linear algebra person might say, whatever we put in here, let's make it linearly independent from these, so we at least have a full set of vectors. So we have a basis for R3. That's another idea to fill it out. Okay? I'll propose another idea. So if you think about, and I'll just tell you what it is. So I actually didn't know what it would produce, but I tested it this morning on the bus, and it was a little bit underwhelming what vector it produced, but I think it's a good principle. So think of this. Think of starting with a matrix and doing Gaussian elimination on it, and capturing it by matrix products. In other words, we're going towards LU. So how does that work? The first operation is represented with this elementary matrix. Then the next, and the next, and the next. So I will actually summarize the fact that there may be many, many steps by putting dot, dot, dot here, right? Except in LU, we only took it as far as Gaussian elimination, which is to identify the pivots and eliminate everything below the pivots, so you end up with the matrix U. But here I'm suggesting taking more steps, putting Jordan back substitution steps into this process until you end up with the row-reduced echelon form of the matrix. So taking Gaussian elimination not only as far as U, but as far as it can go, which is to bring the matrix to its row-reduced echelon form, and calling this the matrix A. So the original matrix is the matrix A. After you do everything you can possibly do, you end up with the row-reduced echelon form, and you summarize all of your Gaussian elimination steps by the matrix, and we will call that C inverse. Right? So multiply these matrices together, call that C inverse, and then C inverse A equals R. In other words, A equals CR. So call the matrix C, I don't know, I'm going to write it in, as the reconstruction of all the Gaussian elimination steps that you take on your way to the row-reduced echelon form. So I did that this morning, and it turns out that this column ends up being 0, 0, 1. Right? So it's a little bit underwhelming, but at least it is a principled way to do it. And then I tried a few other combinations that involve row switches, in which case you might end up with 1, 0, 0, 0, 1, 0, and so on. But that's a nice, unique way of building this matrix.
Wait, this also means
filling out this matrix.
A times.
Hold on one second. Let me criticize. I'll first criticize this approach. What's bad about this approach is that this matrix no longer represents the column space of the original matrix A. right? Only the first two columns represent the column space of the matrix A, and this fills it out to a basis to R3. Okay, and then of course this gets erased by the zeros in the matrix R. Anyway, thanks for coming and letting me speak about this great topic. And it's actually Strang's birthday in a couple of days, so this will be like a birthday present.
Are you gonna send him the video for his birthday? Drop the
Of
video for his
course.
birthday?
Yeah, of course.
Unedited.
Happy birthday.
And happy birthday.